Hello everyone and welcome. As I must have told earlier that I am a power electronics engineer, and when I started learning motor control, I had zero idea about how motors work. I had actually forgotten whatever I learned in the university. So I had to go back and learn about motors again. That is exactly what we are going to do in this video. We are going to see what is a rotating magnetic field, how do induction motors work, what is a brushless DC motor, what are reluctance motors, and what is the basic principle behind operation of each of these motors. So let us get started. In the last video we introduced Faraday's law and Lorentz law and made a linear motor work. We will now use these laws to spin a motor. There are two bar magnets with their respective north and south poles facing each other. The field lines will travel from north to south. We also have a coil wrapped around a core and we can push current in these windings. When the current flows in the coil, it will develop its own magnetic field, and we can denote this field with north and south poles. The direction of the field is given by the right hand thumb rule, which we discussed in the previous video. So we now have two magnetic fields present. One is due to the bar magnets and the other is produced by the current in the coil. These two fields interact with each other such that the north and south poles of the coil get aligned with the south and north poles of the magnets. We could complete just a quarter rotation and we need to think of how to successfully complete one full rotation. What we can do is reverse the direction of the current in the coil, and that will reverse the direction of the poles. This will also flip the coil by 180 degrees since the north and south poles attract each other. If we continue reversing the direction of the current in a specific fashion, it will keep flipping the north and south poles, which will rotate the coil in turn and we can create a spinning motion. It sounds simple, right? Well, it's a bit complicated than what we just discussed. The question here is, how do we reverse this direction of current? One of the ways is to use mechanical techniques with the help of carbon brushes, and these motors are also called brushed DC motors. But what we are interested in are the ones which change the direction of current using some electronics. They are also called as AC motors. In this video and in the rest of the series, we will focus on AC motors and how to control them. There are plenty of variations among AC motors, so let's have a look at them. One of the earliest discoveries was the induction motor. The stator or the stationary part consists of a three-phase winding into which we can push current. A and A' are connected to the same phase, but they are wound in opposite directions. This will create opposite poles for these two windings. Similarly, B and C are connected to the other two phases. We will feed sinusoidal current to the three-phase winding in a fashion that the net magnetic field is constant in magnitude and it is rotating in space. This is also called the rotating magnetic field and it is shown by the red arrow. Let's look at this animation to illustrate this concept. Here are the three-phase sinusoidal currents and red, blue and green vectors represent the magnetic field produced by these currents. The black vector is the net magnetic field and we can see that its magnitude is constant but it is rotating in space. The direction of this vector denotes the direction of the effective magnetic field and the length of the vector denotes how strong it is. It is fine if you did not get this right now because we are going to understand this in detail in future videos. But for now, we can remember that using three-phase sinusoidal current, we can create a rotating magnetic field which is constant in magnitude but rotating in space. But why do we need three phases? It is important to produce a constant field, otherwise we will see a torque ripple which is not desired. A single phase winding cannot produce a field which is both constant as well as rotating in space. Hence we use the three phases to do so. Now let's place a closed loop conductor in this field. What this conductor will see is a varying magnetic field as it is rotating. In the last video, we saw that if we have a varying magnetic field, it induces current in a closed circuit. This current will produce a field of its own, shown by the green arrow. The field will always try to align with the rotating magnetic field so as to reduce the change in flux. We discussed this in the previous video when we understood the importance of negative sign in the Faraday's law. So what will happen is, since we have a rotating magnetic field, the conductors will always try to catch up with the stator field, and hence we have a spinning motion. This is the basic principle of induction motor. There are many amazing videos that explain the induction motor in depth with very nice animations, so we are not going to discuss about it in this video, but what we should understand is, the stator field is created because of the current flowing in the windings, whereas a rotor field is created by the induced current in the conductors. We should also observe that the rotor in induction motor does not have any windings or magnets, it just has conductors. And that is the beauty of induction motors. Now let's look at the brushless DC motors and how they are different from induction motors. Even though it has a name DC in it, I still consider it as an AC motor because we need some electronics to convert the DC supply to AC before feeding it to the motor. Some people might disagree with this terminology, but what matters is we understand how this motor works. The stator is similar. We have three-phase windings and we have a rotating magnetic field. Instead of a closed loop conductor as in the previous case, now we have a steel rotor with two magnets placed on the surface of the rotor. The net effective magnetic field is shown by the yellow arrow. This field will try to align with the rotating magnetic field as it will attract. We are not going into the details but just getting an idea of how the fields interact. We have a question here. Do we always need two different fields to produce torque? Think about it for a moment before you listen to the answer. Well, the answer to this is no. There is an ingenious way to make the motor spin with just one magnetic field. We have to make use of the magnetic reluctance of the circuit. But what is this magnetic reluctance? Just like in an electrical circuit, we have a resistor which obstructs flow of current. We have magnetic reluctance which obstructs the flow of flux path. Good conductors like copper, aluminium offer little resistance. Similarly, ferromagnetic materials like iron, cobalt offer little reluctance to the flux path. Materials such as air, permanent magnets, and all other non-ferromagnetic materials offer high reluctance. Yes, permanent magnets also offer high reluctance. This is because it does not change its orientation or it is not easily magnetized or demagnetized by an external electromagnetic field. We will also note one important property of flux. It tends to take the path of least reluctance, and that creates the force or the torque. To understand this, let's consider this setup. We have a rotor steel rod placed inside a stator with only one winding. If we energize this winding, the flux will flow from north to south. Flux will not flow directly through air gap as shown. Rather, it will take the path of the steel as it has low reluctance compared to the air gap and it will return using the stator. But the field lines in the steel rod will create poles in the rotor steel such that it attracts the steel so as to further minimize this reluctance. And this is how torque is generated. Now imagine a rotor made entirely of steel. The reluctance of the rotor seen from any direction is the same because the flux will see same amount of steel. But if we now remove some sections of the steel from the rotor, we have created air gaps in the structure. We know that the air gaps offer high reluctance than steel. So the reluctance of the rotor from different angles is different. This angle will see more air gap compared to this angle. So we will have more reluctance here and less over here. The more the steel seen by the flux path, the lesser the reluctance. But where is this flux? So let us add a three-phase windings back and create the rotating magnetic field. The rotor position, which sees the least amount of reluctance, will try to align with the stator field direction. Thus we produced a torque with just a single magnetic field and a variable reluctance. If we rotate this magnetic field, the rotor will also rotate so as to minimize the reluctance to the flux path. Hence we have created the spinning motion. Isn't this great? I think it's brilliant. This property of the rotor where the reluctance is dependent on rotor angle, is called saliency. If the reluctance is independent of the rotor angle, then the rotor is called non-salient. We can actually do one more trick in designing these motors. Let's have a look at the brushless motor again. Instead of placing the magnets on the surface of the rotor, what if we bury it in the rotor? What we have effectively done is change the reluctance of the rotor. This is because permanent magnets are equivalent to the air gap in terms of reluctance. Hence, this rotor also behaves as a salient rotor. Over here, we have used two principles to produce torque. The first principle uses two interacting fields, one of which is produced by the magnets. We will call this as magnetic torque or the electromagnetic torque, and the other due to the effect of saliency, which we'll call it as a reluctance torque. Since we are using the combination of both these torques, we are able to create more torque without increasing the size of the rotor. Hence, we have achieved a higher torque density. Such motors are called the interior permanent magnet motors. These magnets can be placed in a lot of different ways. It leads to different amount of saliency and we'll get different kinds of performance from these rotors. But this rotor is difficult to manufacture compared to the surface mount rotor. Actually, there is no single motor that wins over the other. There are a lot of factors like cost, power density, availability of magnets, ease of manufacturing, and of course the application. So choose your motors wisely. Most of these motors can be controlled by a control algorithm called field-oriented control. We will specifically discuss FOC for brushless motors with sinusoidal windings. I will get into further details in the next video. But before we end this video, we should remember the important things that we learned. We saw how three-phase sinusoidal currents can create a rotating magnetic field. If we use a closed-loop conductor with the stator, then we get the induction motor. If this is replaced by the surface mount magnets, we get the brushless DC motors. We can also use a salient rotor to form the reluctance motor. And lastly, if we combine the use of magnets and saliency, we get the IPM motor.